So yeah, the floor is yours.
Okay, thank you very much for giving me an opportunity to give a talk here. So let's start. And I will start with a very well-known example so that people that will join later won't regret that they have missed something. So we consider a quadratic polynomial with complex coefficients. We work everywhere all over complex numbers. And a very essential question that one can ask about this polynomial is whether it has a multiple root, or for what kind of coefficients b0, b1, b2 would such a polynomial have a multiple root. And the answer is known from high school. There is this expression which we all called discriminant without probably realizing what it is in general. b1 squared minus 4b0, b2 should vanish so that this polynomial has a multiple root. In other words, we can consider the set A, which is 1, 0, 2, some list of degrees, right, in a one-dimensional lattice, and consider all univariate polynomials with degrees listed in this set. So just as written. And since every polynomial is uniquely defined by the tuple of its monomials, we can think of this space as just C3 in this case. And in this space CA, what we would refer as the classical discriminant would be just the hypersurface given by this polynomial, okay? We can generalize all this. We can consider an arbitrary set A in, say, one-dimensional lattice. And again, the set of all polynomials with degrees in this set A. And then we would refer to the discriminant or classical, as opposed to the Morse discriminant that we'll talk about later. That would be the closure of all polynomials that would have a non-zero multiple root, or in other words, at some non-zero point, that would have, so the polynomial together with its partial derivatives would vanish. Why am I interested in non-zero multiple roots? Well, this is quite easy to explain. Suppose you have your set A, which only consists of positive numbers and is located somewhere far from zero, then all of your polynomials would have a multiple root 0. It's not very interesting. So in order to not deal with this part, it's a trivial part, we are interested in the set as I defined. Of course, one can define the discriminant in more generality. One can consider multivariate polynomials, and then would be interested in the points where the polynomial together with all of its partial derivatives would vanish. Anyway, it's pretty hard / impossible for quite a very big set A to compute explicitly the discriminant as the polynomial. And therefore, in order to get some information about it, we might need to sacrifice something because, well, some little amount of information is still better than nothing. So as a motivating example, I would say, suppose just on your computer, you would have like a long polynomial in one variable with some super nasty coefficients and occupying many, many lines, and you would not know what to do with it. Best thing you could do in this situation is at least try to see the degree, right? That would tell you at least how many roots you can expect. So we would do the same thing. We would speak about the Newton polytopes of the polynomials, and let me quickly remind you what it is. So suppose we have a polynomial. Here it's a polynomial in two variables, and in general Laurent polynomials. So we would allow we will allow monomials to have negative degree as well. So then we would take the lattice of the same dimension as the number of variables, and on this lattice we would mark the finite set of points, which we'll call the support of your Laurent polynomial. And the support is very kind of easy to construct. You take for every monomial, you take its degree, and just mark the point with the same coordinates on your plane here. So say there is the point -1, 2, which is associated with monomial x1 inverse x2 squared, or there is point 0, 0, which comes with this term 5, and so on. So you get a finite set, which we call support. And if you take its convex hull, then you will get what we will call Newton polytope, or in this case, Newton polygon. And even though we lose a lot of information about the polynomial passing from the polynomial itself to its Newton polytope, we lose information about coefficients, we lose information about all the monomials such that the corresponding point of the support set lies inside your polytope. Still, it helps to recover a lot of information about the variety given by this polynomial. If you have ever heard of theorems like Bernstein-Kushnirenko, then you might know what I mean. If not, well, that's a good reason to dig into that. One property of Newton polytopes that we will actually use in this talk is that they behave nice with respect to multiplication. So if you multiply two polynomials, then the Newton polytope of their product is the Minkowski sum of the Newton polytopes of the multiples. And as a special case, if you multiply a polynomial by a monomial, then your polytope actually doesn't change, it just gets shifted on the plane. That's all. Now, coming back to the question about computing the discriminant explicitly, I can just say that, say, in one-dimensional case, if you would still need, for some reason, to do it by hand, you could use the following trick. I hope from undergraduate studies, you know what resultant is of, say, two polynomials and one variables. That's also going to give some polynomial in their coefficients that vanishes whenever the corresponding polynomials have a common root. And one can compute the resultant explicitly using the so-called Sylvester formula. The expression will be a determinant of some big matrix, and the bigger the sets, the bigger the matrix. Say even in the case below, it's already quite big, even though it's pretty trivial. Nevertheless, you can compute the resultant of your polynomial together with its partial derivative, and you would expect to get what you need, because basically discriminant also would contain polynomials that vanish somewhere together with their derivative. So let's do it for A012, and then what we would get, we would get this nice expression, which is almost what we would like, except for there is some parasitic multiple. Something that actually doesn't have much to do with the discriminant, because, okay, vanishing of B0 would mean that there is just a root outside of the algebraic torus, and vanishing of B2 would mean that your polynomial stopped being quadratic. But nevertheless, a polynomial obtained this way, which is, as I said again, substituting polynomial together with its partial derivatives into the sparse resultant. It has a special name, and it's called A-discriminant. In the univariate case, which we will mostly cover by this talk, that means that the set A, the support set, is one-dimensional. The A-discriminant is a discriminant that we are interested in, sort of, times a monomial. Therefore, up to a shift, as we have discussed before, that means that the Newton polytopes are sort of the same. So it's really literally a shift. In general, it's not the case, but it's still true that the Newton polytope of the A-discriminant is the Newton polytope of A-discriminant plus some other polytope, which, I mean, what it is, it's sort of studied and still allows to do some computations, but makes the situation much more nasty, and I don't want to touch it today. As you can guess, we can, instead of trying to compute the discriminant, compute its Newton polytope. And it turned out that actually in univariate case, you don't feel that difference much. In multivariate case, you will feel this difference. That describing the Newton polytope of A-discriminant is much more tricky and hard, but is related to describing the Newton polytope of the A-determinant, which turns out to be actually super nice. So, but since we today focus on the univariate case, the result by Gelfand, Kapranov, Zelevinsky stated for the A-determinant also makes sense for A-discriminant, because these Newton polytopes will be sort of the same up to a shift. The result states that vertices of the Newton polytope of the A-determinant are in one-to-one correspondence with the subdivisions of the convex hull of A I remind you that A is one-dimensional, so the convex hull is an interval. But subdivisions, this is something that we know from analysis and many constructions, subdivisions of an interval. But we are concerned not about all subdivisions, but only those that have endpoints inside of the support set A. And the best part of this theorem is that if I have such a subdivision, I can just look at it and purely combinatorially compute the corresponding vertex of the Newton polytope. As I say, vertices are in one-to-one correspondence with subdivisions. Let me give you an example. So if A is equal to 1, 0, 2, we already know what the A-discriminant is. It's this expression. So the Newton polytope is going to be an interval because there are going to be only two monomials. And there are two subdivisions of the interval from 0 to 2 with vertices in 0, 1, 2. Basically, there are two options. You either include 1 as an endpoint and get a subdivision from 0 to 1 and 1 to 2, or not include 1, and then you get the entire interval from 0 to 2. Looking at these subdivisions, we can produce the coordinates of the vertices. Let me show you how. So in this case, say we have 3 elements in the set. Therefore, we will have 3 coordinates of the vertices. Our polytope is going to be in 3-dimensional space, as we have discussed before. So we look at the leftmost point, 0. We look for the total length of all intervals such that this one is an endpoint. So here, this one is an endpoint only of this interval of length 1. So we put 1 here. Then this one is an endpoint of this interval and this interval. Total length is 2. So we get 2 here. And this one is only the endpoint of this interval of length 1. Therefore, we put 1 here. And here, well, you do the same thing. This one is the endpoint of this interval of length 2. This one is not endpoint. Therefore, we get 0. And 2 is an endpoint of this interval of length 2 again. So we put 2. And then to this point corresponds the monomial b0, b1 squared, b2. To this point, b0 squared, b2 squared. So everything works fine. And if we wanted to just find the Newton polytope of the discriminant, then we would have to just subtract 1, 0, 1 from each of these points. You can see it from here. In general, you can, as I said, the Newton polytope of the discriminant and Newton polytope of the A-discriminant would differ by a shift. And you can determine this shift by looking at the set A. It's always going to be the term of lowest degree times, so in some power, times the coefficient, so the highest degree coefficient, also in some power, which can be determined by the geometry of the set A. But it doesn't matter in our story. One more example, which we will also need later, is a discriminant of a cubic polynomial. It's much harder to reproduce to know it by heart. But you can sort of recognize the coefficients, and the Newton polytope is going to be just this nice, lovely polygon. There are only 4 subdivisions of the interval from 0 to 3 with vertices in 0, 1 to 3. So it's all very easy and nice. In general, as I said, so there is this construction of polytopes whose vertices are in one-to-one correspondence with subdivisions are a special case of the so-called secondary polytopes. And secondary polytopes generalize a lot of families of very nice polytopes, which are of interest to algebraic geometers, combinatorialists, people doing combinatorics, sorry, and people doing representations theory and so on. And if you haven't seen them much before, you can dig into the book by Gelfand, Kapranov, and Zelevinsky. They have a dedicated chapter about secondary polytopes, and it's absolutely beautiful. I also need to say one more thing. So as I said, in univariate case, we have this theorem, and everything is nice about it. In multidimensional case, everything is true except for subdivisions would be changed into convex triangulations of the convex hull of A with vertices in A. And moreover, if in multivariate case, you would love to reformulate this theorem not for the A-determinant, but for A-discriminant, then one-to-one correspondence will be replaced by surjection. And that's also important for the future. So anyway, this is one of the examples when things become not one-dimensional. So the set A are just the vertices of a hexagon, and the vertices of this beautiful polytope correspond to the convex triangulations of this hexagon. So please look at it if you haven't yet. Now I can pass to the problem that I've been working on within my PhD project, and I was studying the so-called Morse discriminant. Let me tell you what it is. So again, we are in the setting when we have some fixed set A. So we consider the set of all polynomials with support A in one variable. And we are interested in the following two strata, generally speaking, of codimension 1, which are called caustic and Maxwell stratum. Caustic contains polynomials that have a degenerate critical point, if viewed as maps from the algebraic torus to C. So basically in this picture, as you can see, so all we need from such a polynomial that its first derivative and its second derivative vanish. Maxwell stratum contains polynomials that have a pair of coinciding critical values taking at distinct points, just like drawn here. A polynomial is called Morse if none of this happens, and otherwise I call it non-Morse. Maybe it's not the best choice of definitions, but well, that's the one. As I said, usually we expect those strata to be of codimension 1, so they're going to be given by some polynomials. There are going to be some hypersurfaces, and let me give you an example. A is equal to 1, 2, 3, 4. It's the easiest non-trivial example where you can see both of the strata. So the caustic then would be given by polynomial HC, and you can recognize it. You've seen it a couple slides before or something similar. And that's not a coincidence, because I already said that the caustic would contain polynomials such that the first and the second derivatives vanish. So basically what we're speaking about here is a classical discriminant of the derivative, not of the polynomial itself. While for the Maxwell stratum, that actually was the main challenge of this entire project, we cannot say many good things, except for in this easy case, the polynomial is pretty nice. We also can have some algorithms that can allow to compute it explicitly on the computer, but they take a lot of time. The bigger the set A, the longer it takes, let's put it this way. So the problem was to actually try to compute the Newton polytope of the Morse discriminant without computing the Morse discriminant, purely in combinatorial language. And what I call the Morse discriminant is this product, the product Maxwell stratum squared times caustic. You might ask me why. Well, a short answer would be for convenience. A long answer would also be that if you just say we're interested in computing the Newton polytope of the Maxwell stratum, all of the methods I use can be tailored, the formulas will be still explicit, and everything will be fine. So if you want just the Maxwell stratum, you can get it from my methods. But for several reasons, I prefer this product. For A equal to 1, 2, 3, 4, the Newton polytope that I've been speaking about would be a pentagon. This very nice, lovely pentagon, which we can compute explicitly, right? Because we have the polynomials written out. In general, we don't want to write anything out. So how would we tackle this problem? Well, I'm not going to explain how we tackle this problem unless you ask me at the end of the lecture, of the talk. And yes, that is a hint for you if you feel uncomfortable and don't know what to ask me. If we want to compute some polytope, we can equivalently compute its support function. Let me remind what it is. So suppose in Rn we have some convex polytope. Then a support function would be a function that would take as input a covector in the space lying, so in the space dual to the one that contains the polytope, and output would be just the maximum that this covector, considered as a linear function on your polytope, would attain in this polytope. So this is a little example. Suppose this is a triangle in R2 with this lovely vertices, standard simplex, what we would say. Then on the right, we can see the behavior of the support function. So it's a piecewise linear, right? Moreover, so like we can see the connection between the linearity domains of this function and the vertices of the Newton polytope. Let's look at this. So suppose we take a covector lying in this cone. That means that coordinates are non-negative and first coordinate is not less than the second coordinate. Then such a covector lying inside of this cone would attain its maximal value at this vertex. And in order to know this value, all one has to do is to pair this vertex with the covector. So that means that in this cone, this function is linear. The support function is linear. It's going to be like this. And the same one can do like with other cones. And those linearity domains of the support function are in bijection with the vertices of the polytope. Moreover, knowing the coordinates of the vertices of the polytope is exactly the same as knowing the coefficients of this piecewise linear function in each of its linearity domains. One more remark that I have to do here, make here is that if you take a covector at random, then it will probably end up inside one of those linearity domains. And that's why it will end up taking the maximal value at one of the vertices of your polytope, and you really need to try much harder to find a covector such that the maximal value would be attained on the edge or on the entire polytope. Okay, one more remark I have to make about support function is that if the dimension of the ambient space is strictly bigger than the dimension of the polytope, then all I said is true, except for, no, not even except for, moreover, as a bonus, what we get is that all of these linearity domains of the support function would contain a common subspace of complementary dimension to the dimension of the polytope. We would need probably this thing if you ask me extra questions at the end. But nevertheless, let's come back to at least understanding the structure of the answer to this question. And for this, we will actually need the tropical language. We wouldn't need that to find this answer. So I didn't use it in computations. I used a completely different approach with some algebraic geometry, singularity theory, combinatorics flavor. But this is a very elegant way to state the answers. So let me quickly remind you the basics. So we would work over tropical numbers. So this is the tropical semi-ring, real numbers with minus infinity added, and two operations, tropical addition and tropical multiplication, with tropical multiplication being just usual addition, and tropical addition being very weird. So with a pair of distinct numbers, it would associate their maximum. If those numbers are the same, then the answer would be an entire interval from minus infinity to this number. If you think it's weird, you can think of what happens to degrees of polynomials in one variable when you add them and multiply them. If you multiply them, then their degrees add. If you add them, then the answer depends. If the degrees are different, then the degree of the sum is going to be the maximum of the two. But if all you know that the degrees are the same and you don't know coefficients, then as an answer you only can shrug your shoulders because you don't know how many terms can cancel out when you add these two polynomials. And basically this is an analog of shrugging shoulders. A tropical Laurent polynomial with given support is a tropical sum of tropical monomials. Very elegant, very simple. And if you look at this expression and open up all the notation, use a slight abuse of notation, forgetting for a second about this multi-valued story, Then basically what we would be interested in the maximum of some list of affine linear functions. That's why we really like working with tropical objects, because they're lovely and nice and easy. A tropical root of a tropical polynomial, and here everything is in one variable. So it's a point where at least two monomials attain this maximal value, which I call critical value. If for some reason what I say seems confusing, please stay with me. In a couple seconds, minutes, you will see a picture and everything will become much more clear. But before I draw any pictures, let me introduce one more construction. So I don't want us to get lost in this tropical world without remembering that all we need to do is to compute some support function. So since we're computing the support function of the Newton polytope of the discriminant or Morse discriminant, we take a covector as an input. We should do something with it. And what we can do, this slide is about associating a tropical polynomial with a covector. Let's view it this way. So your covector lies in the space dual to our cardinality of A, right? So because there will be cardinality of A coordinates in that space, right? That's why the coordinates are indexed by the set A. That means that you can see the covector actually as a function from your support set to R. And if you understand what I say, then you can imagine that now we can easily construct a tropical polynomial with support A and coefficients which are the coordinates of your covector. If that was not clear, let's look at an example. So if we take A, this wonderful set, -3, -1, 1, 2, 4, a set of 5 elements, so then the corresponding covectors would be in 5-dimensional space. There will be 5 covectors. And with the covector 3, 5, 2, 5, 1, I would associate the tropical polynomial, which in this form would be as follows. We would have to take, so here there are the slopes of this affine linear function, and here are the constant terms. So it's going to be -3x plus 3, -1 times x plus 5, and so on. So again, covector, tropical polynomial, very easy. Now let's draw. So if you want to draw a graph of a tropical polynomial in one variable, what do you have to do? Well, you can draw all these affine linear functions, all their graphs, one by one. You've done it. Good. So now we can take the max. Again, very easy. And then you immediately find those points where the slopes change. And this is exactly what the roots are going to be. So the operation of addition is multivalued. Therefore, there should be legs, vertical legs to -infinity from all of these points. So the heights of these points are going to be the critical values, what they call. And well, these 3 points are going to be the tropical roots. These gray lines are a reminder that sometimes a monomial, tropical monomial, may never get to the top. And in classical case, they don't matter. Even as far as I know, that like they're called insignificant or something like that in some literature. And within my project, somehow there was the fact that apparently insignificant monomials lives matter. So that's a reason in itself, to dig into that, I think. So now I want to actually give you the answer for the classical case, because we know the answer in terms of the secondary polytope story, but I can reformulate in the tropical language so that you understand the flavor. So what the thing is that we can come up with a notion of a smooth tropical polynomial. Very interesting to use the word smooth to an object which is like, piecewise linear, but nevertheless. And this is a perfect example of a smooth tropical polynomial. because at every root, there are exactly 2 monomials that attain the maximal value. Not 3, not 5. So this is a smooth tropical polynomial. Apparently, a shape of a smooth tropical polynomial is the same thing as the subdivision. And we have discussed subdivisions, right? We have a bijection between subdivisions and the vertices of the Newton polytope. So this is a semi-example. There are no numbers here, but still. So suppose we have some set A with 6 elements, and we consider tropical polynomials. And let's consider tropical polynomial whose graph we have already seen. For your convenience, I even mark which monomials dominate at each of the parts so that you can really see how it works. So actually, from such a polynomial, I can read the following data. I can look at which slopes form the top part of this curve. And what I get is A0, A3, A4, A5. I write them down in the list, and I can consider the corresponding subdivision. So a subdivision that would contain exactly these endpoints. So I can take a smooth tropical polynomial and read a subdivision. Now let's play a bit. Let's make this coefficient slightly larger. Okay, nothing yet changed. Let's make it slightly larger. And what we get? Well, we get a very interesting case where the polynomial stops being smooth, because at this point, there are 3 monomials attaining the same maximal value. If you ask me what kind of subdivision can we associate with that, I will say, I don't know, because I don't know what to do with this point A1. Should I include it? Should I not? So that's kind of ambiguous. That's kind of like, a wall. But if we cross this wall, then we end up in some new configuration at some new smooth tropical polynomial of a different shape. Here, there is no doubt that I should just add A1 into my subdivision, because A1 starts to participate in the top part of the tropical curve. This teaches us a lot of things. First of all, it teaches us, since it's a bit of combinatoric seminar, right? So we would be interested somewhat in the combinatorics of the secondary polytope. And actually, this gives you intuition behind how 2 neighboring vertices of the secondary polytopes are connected by an edge. This cartoon gives you this notion. But also, it allows us to restate the classical result by Gelfand, Kapranov, and Zelevinsky in the following way. Again, so suppose we would want to describe the Newton polytope of the classical discriminant. It would be the same as to compute its support function. And as I discussed, that a generic covector would always attain a maximal value at some vertex of the polytope we are wondering about. Or in other words, it would land into one of these full dimensional cones, which are linearity domains of your support function. And the question would be, for every covector, which linearity domain it is, and how does the support function behave there? And what we can do, I think you can guess the pattern. So we take this generic covector, we associate a tropical polynomial with it, and if it's generic, if it satisfies certain genericity conditions, this tropical polynomial is smooth. And then from a smooth tropical polynomial, we can read the data, which is subdivision, and we can only read it if the polynomial is smooth. And then looking at subdivision, the way I explained you in the beginning of the lecture, I can restore linearity domain, or in other words, the vertex of the Newton polytope of the discriminant. So for non-Morse tropical polynomials, you can understand now what kind of the answer I'm going to tell you. So I will have, instead of coming up with a notion of a smooth tropical polynomial, to come up with a notion of Morse tropical polynomial. And here is an explanation. Actually, this slide shows you not Morse tropical polynomials, but non-Morse tropical polynomials. So a tropical polynomial can be not Morse due to the one of the 2 reasons. First one, I would show in the right. So this is if it gets to the so-called tropical Maxwell stratum. That means that at two roots, the critical values attained at those roots coincide. So this kind of reminds you, I think, of the classical story. That's why the name is like that. So that's why I call this situation getting on a tropical Maxwell stratum. And when it comes to tropical caustic, it might be slightly more tricky, but the idea is as follows. At every root, we definitely know that there are two monomials that attain the same value, the maximal value, right? So these two monomials that kind of show you the change of the slope. But what if at the root, some other pair of monomials attains the same value, just like drawn here? The ones that dominate at any point, or those that don't, it doesn't matter. So it's just like a classical representative of such a bad situation. Then, if such a thing happens, I say that my polynomial belongs to the tropical caustic. All of these notions are work in progress, so I might review them at some point. But for now, let's stick to those. And now, as you can guess, the format on the answer in the story that I've been studying would be the following. We want to compute the Newton polytope of the Morse discriminant now. And again, it's the same thing as to compute its support function. And again, a generic covector would attain a maximal value at a vertex, or otherwise belong to some full dimensional cone of the support function. This we all know. And again, the question would be how to know for every covector in which linearity domain it got and how to find the corresponding coefficients. Well, the answer is as follows. You take your covector, you can associate a tropical polynomial with it, and if it satisfies certain genericity conditions, which we came up with using some completely different method, which you can ask me about later, this polynomial will turn out to be Morse. And if it's Morse, I can read a certain tuple of data, which is slightly more complicated than just the subdivision, though subdivision is a part of it. Once I have this data, I can explicitly, I'm not going to show you any formulas, you can look them in my preprint, but I can write down the coordinates of the corresponding vertex of the Newton polytope of the Morse discriminant. Let me give you a little glimpse of what I mean by combinatorial data. I don't want you to concentrate on how I write it down, on the format of this data, just only on what it is. So this is an example. This is the support set and the covector that we have seen actually before when I gave you an example of how to associate a tropical polynomial with a covector. And I have not only associated a tropical polynomial, but I have also made its graph. And since I knew what I was doing, this polynomial is Morse. And what kind of data can I get from it? First of all, subdivision, as I already said, we just write down those slopes that participate in the top part of the tropical curve. This is -3, -1, 1 to 4. Very good. The next piece of information is the order from lowest to highest of the critical values attained at the roots. I just really need to know that, say, middle one is lowest, the left one is then second lowest, and the right one is highest. In this case, in general, just their order. And you can see that this information I can only get if my polynomial does not belong to the Maxwell stratum. Because if it does, then two critical values are the same height. So I don't know which one goes first. Okay, and finally, we need to somehow employ the fact that this polynomial does not belong to tropical caustic. For that, what you do is you read the third part of the data. So you know that at every root, there are two monomials that attain the maximal value. You are not interested in those, but you can look at what happens to other monomials at this root. You can evaluate them and just record the order from highest to lowest of all those values. So if your polynomial belongs to the tropical caustic, you can't do this because there would be a pair of monomials that would intersect this vertical leg somewhere below the critical value. And you would not be able again to say which one is highest, which one is lowest. But if your polynomial does not belong to the tropical caustic, then you can read this information in which format, it doesn't matter. But you can do this, and using this tuple of information, you can plug stuff into some formula, which I have found, and just be happy. Find the vertices of the corresponding vertex. So the result that I got was that I established a surjection between the set of all possible combinatorial types of Morse tropical polynomials with the given support set A and the vertices of the Newton polytope of the Morse discriminant. And I have to emphasize that this is a surjection. So there might be, and there certainly are, cases when the same different combinatorial types of Morse tropical polynomials, so different tuples of data, give you the same vertex. But as long as you just want to enumerate all the vertices one by one, that doesn't matter. So you can just play with all possible types of Morse tropical polynomials with given support and just find all the vertices. So coming back to the example, when A is 1, 2, 3, 4.
Do you know the fibers then?
Hey,
Sorry?
Can you hear me?
Now I can, but before
Okay,
it was.
so what are the? Do you know the fibers then? In the case that you're not in the case that you're not injected, are they in some way combinatorially described, or are they?
Unfortunately, I wasn't able yet to combinatorially describe those. It's so there are certain like kind of cases that I can classify. So some rules of parallelogram or whatever I call it, but I don't know yet how to proceed in general. And that's an interesting question that intrigues me a lot in some sense. But nevertheless, I'm about to finish, and then I might say a couple more words about your question. Thank you for asking it. So here I just say the same polytope that we have seen before. I just chose some configuration for every vertex, and basically that's it. So I can view in my deformed mind, I can now view those tuples of coordinates, not just like tuples of coordinates, but as some tropical curve with extra information. So yeah, so for the talk, that's all I wanted to say. Thank you very much for your attention. You're welcome to ask me questions, and also see my preprint for more details, explicit formulas, proofs, and the methods that I used.
All right. Thank you very much for the talk. There already was one question.
Yeah, yeah. So what I wanted just to add concerning this question is that this question intrigues me a lot, because as you see in the classical case, in general, also like the result says that, okay, there is this surjection between this beautiful set of subdivisions or triangulations, convex triangulations. So also a surjection with the vertices of the Newton polytope of the discriminant. So that means that there is some very big, very nice polytope, the secondary polytope, which kind of contains like all these configurations, and kind of, yes, some of them would give you the same vertex. They would be glued somehow when you do the Minkowski subtraction from the Newton polytope of the A-determinant and these parasitic terms. So here, that also intrigues me a lot, because what I am hoping to find would be the analog, and such a polytope, also such a big polytope, that would somehow like enumerate like all those configurations and kind of be maybe Newton polytope of something like an analog of A determinant or something, or just be a beautiful combinatorial construction in its own. But I think this would help me to actually understand those fibers better. So there's literally what vertices get glued and what not. Because if I'm lucky enough that it turns out in fact to be a Newton polytope of some polynomial, say, that contains my Morse discriminant as a one of the multiples, then I would know at least what I would have to subtract in terms of Minkowski to actually get each of the vertices. And actually, this will give me more information. This is what I'm hoping to get, but unfortunately, I wasn't yet able. But that's really what I would love to do in the future. Like that's the question that still makes my heart beat faster. Let's put it this way.
All right. Are there any other questions? So I have a very small one. You said that you also had some algorithms for that were slow. What do you mean by slow? So did you implement them and they weren't running too fast, or is it like some theoretical bound on the runtime? Or
so the thing is that at least the algorithm that I know would employ how do you call it, like symmetric so like, you know, writing a symmetric polynomial as the polynomial in elementary symmetric polynomials.
Mm-hmm.
And that takes a long time in general.
Okay, so that is known that that's a hard
No, I
problem.
mean, yeah, it's a
Okay.
yeah.
Okay. Any other questions? That doesn't seem to be the case. So thank you again, Arina.
Well,
okay.
Maybe, but I mean, okay, I think it's a longer question. I think there's another speaker coming now, right?
So
is she already here?
She's not here yet, but we still have 12 minutes. So
okay. I mean, okay, but I also want to get the coffee. But have you ever thought, I mean, okay, you already said a little bit about smooth polynomials and subdivisions, and I mean, of course, that's related to resolutions of singularities, right? I mean, I don't know, I looked at classical Ronaka proof or the Knudsen, Kempf, what, I mean, the class, I mean, Knudsen, Kempf, Sandonard, Waterman, and Mumford in alphabetical order.
I haven't looked at it, so if your question is long, that I better.
Okay, I wanted to ask whether somehow, of course, you can do all the same, you can do similar things in log geometry, and I wanted to ask whether, in some sense, you could make sense of some of these Morse polynomials in log geometry. But okay, so then I mean it's a further question that we can discuss maybe another time. All right. Then I would get a coffee before the next one. Thank you very much.
Okay, yeah. So thanks again. I will stop the recording.